我们接下来的嘉宾是深度学习之父、图灵奖得主 Professor Geoffrey Hinton. Hi, Professor Hinton. It's a great honor to have you today with us. In May, you left Google to be able to speak more freely about the existential risk from AI. I've heard that following that decision, there was a point in which you were receiving invites for interviews and media once every few seconds. So we feel extremely fortunate that you have been able to find time to speak to us. Professor Hinton, can you hear us? Sorry, we can't hear you.
Yes, I can hear you.
That's great. I will hand it over to you now to deliver our closing keynote.
Can you see my screen? Okay. What I'm going to talk about today is the research that led me to believe that superintelligence is much closer than I imagined. Now, I'm not getting my slides on my screen, so I can't advance them. Okay, I'm going to stop the share. Can you still see my screen?
We can see you, but not the PowerPoint.
Okay.
Now we can see the first page of the slide.
Okay, good. So there's two questions I want to talk about, and I'm going to focus almost entirely on the first one, which is, will artificial neural networks soon be more intelligent than real ones? Like I said, I'm going to describe the research that led me to conclude that this may happen quite soon. Right at the end, I'll talk a little bit about whether we can stay in control of superintelligent AI, but that's not what the talk's going to be about. So in conventional computing, computers are designed to follow instructions precisely. We can run exactly the same programs or the same neural nets on different physical pieces of hardware because they're designed to follow instructions precisely. And this means that the knowledge in the program or in the weights of a neural net is immortal. It doesn't depend on any particular piece of hardware. Now, there's a high cost to achieving this immortality. We have to run transistors at high power so they behave digitally. And we can't make use of all the rich analog and highly variable properties of the hardware. So the reason digital computers exist and the reason they follow instructions precisely is because they were designed so that we would look at a problem, we would figure out what steps you needed to take to solve the problem, and then we'd tell the computer to take those steps. But that's changed, and we now have a different way of getting computers to do things, and that is learning from examples. We just show them what we want them to do. And because of this change in how you get computers to do what you want, it's now possible to abandon the most fundamental principle of computer science, which is that the software should be separable from the hardware. So before we abandon it, let's just go over why it's such a good principle. Because of that separability, we can run the same program on different hardware. We can also worry about the properties of programs and do research on the properties of programs or neural nets without worrying about electronics. And that's why you can have computer science departments that are different from electrical engineering departments. If we do give up on the separation of software and hardware, we get something I call mortal computation. And it obviously has big disadvantages, but it also has some huge advantages. And so I started investigating mortal computation in order to be able to run things like large language models for much less energy, and in particular to be able to train them using much less energy. So the big benefits we get from giving up on immortality, that is giving up on the separation of hardware and software, are we could have huge energy savings because we could use very low power analog computation. And that's what the brain is doing. It does have 1-bit digital computation because neurons either fire or don't. But most of the computation is done in analog, and that can be done at very low power. We could also get much cheaper hardware. So at present, hardware has to be fabricated very precisely in 2D. And we could actually have hardware that you just grow in 3D because we don't need to understand exactly the connectivity of the hardware or exactly how each piece of it works. Obviously, to do this would require lots of new nanotechnology, or maybe genetically re-engineering biological neurons, since biological neurons are going to do roughly what we want already. And before I go into all the disadvantages of mortal computation, I want to give you just one example of a computation that can obviously be done much more cheaply by using analog hardware. So if you want to multiply a vector of neural activities by a matrix of weights, and that's the sort of central computation of neural nets, that's where most of the work is. What we do at present is we drive transistors at very high power to represent the bits in a digital representation of the number. And then we perform order n squared operations to multiply two n-bit numbers together. I mean, that might be one operation on the computer, but it's n squared bit operations. The alternative is to implement neural activities as voltages and weights as conductances. And then per unit time, a voltage times the conductance gives you a charge, and charges add themselves up. So now it's obvious how you can multiply a vector of voltages by a matrix of conductances. And this is hugely more energy efficient. Chips already exist that work this way. Unfortunately, what people then do is try and convert the analog answer to digital with an ATG converter, which is very expensive. We'd like to stay entirely in the analog domain if we could. But the problem then is different pieces of hardware will end up computing slightly different things. So the main problem with mortal computation is that the learning procedure has to make use of the particular analog properties of the piece of hardware it's running in without knowing exactly what those properties are, without knowing, for example, the exact function that relates the input to a neuron to the output to the neuron, and perhaps without knowing the connectivity. That means we can't use things like the backpropagation algorithm to get a gradient, because backpropagation needs an exact model of the forward pass. So the question is, what else could we do if we can't use backpropagation? Because we're now all highly reliant on backpropagation. So here's a very simple and obvious learning procedure that people have talked about a lot. You generate a random vector of small temporary perturbations to every weight in the network. And then you measure the change in a global objective function on a mini batch of examples. And then you change the weights permanently by the perturbation vector scaled by the improvement in the injective function. So if the objective function gets worse, you obviously go in the other direction. And the nice thing about this algorithm is that on average, it behaves the same as backpropagation would, because on average, it follows the gradient. The problem with it is that it has very high variance. So the noise created when you choose a random direction to move in, to consider in weight space, scales really badly with the size of the network. And that means this kind of algorithm will work for a small number of connections, but it won't work for big networks. So here's something that works quite a lot better, It still has similar problems, but it's much better than perturbing the weights. And that's to perturb the activities. That is, you consider a random vector of perturbations to the total input to each neuron. And you look to see what happens to your objective function when you make this random perturbation on a mini batch of examples. And you get the difference in the objective function due to this perturbation. And you can then compute how to change each of the incoming weights of the neuron to follow the gradient. So again, it's just a stochastic estimate of the gradient, but it has much less noise than if you perturb the weights. And this algorithm is good enough to learn simple tasks like MNIST. If you use a very, very small learning rate, it behaves exactly like backpropagation, but much slower because you need to use a very small learning rate. If you use a bigger learning rate, it's noisy, but it still works fine for things like MNIST. But it doesn't work well enough to be able to scale it to large neural nets. So what can we do to make it scale? Well, there's two ways to make things scale. So instead of trying to find a learning algorithm that will work for big neural nets, we could try and find objective functions that you can apply to small neural nets. And so the idea is we want to train a big neural net, and what we're going to do is have a lot of little objective functions that apply to small parts of the net. So each small group of neurons has its own local objective function. And now that can use this kind of activity perturbation algorithm to learn a small multi-layer neural net. And it will learn in approximately the same way as backpropagation, but noisier. And then we scale it to much bigger networks by having many more small local groups of neurons. So that leads to the question of where do these objective functions come from? One possibility is to have unsupervised learning on local patches, that is, have many levels of representation of an image, and each level have local patches, and make each local patch on a particular image, make the output of that local neural network try to agree with the average representation produced by all the other local patches. So you're trying to get agreement between what you've extracted from a local patch and what you're extracting from all the other local patches in the same image. So this is classic contrastive learning. You're also trying to disagree with what you extracted for other images at that level. Now, the precise details of how we did this are more complicated, and I'm not going to go into those. But we can make this algorithm work quite well, where each level of representation has several hidden layers, so you can do nonlinear things. The levels learn greedily using activity perturbation, and there's no backpropagation to lower levels. So it's not going to be as powerful as backpropagation because it can't backpropagate through many, many levels. And Meng-Yi Ren put a lot of work into making this algorithm work. And he showed that it can work moderately well. It works probably better than any of the other algorithms proposed that could be realistic, could work in real neural nets. But it's tricky to get it to work, and it's still not as good as backpropagation. And as you make the networks deeper, it gets significantly worse than backpropagation. So I haven't gone into all the details of this method because you can read about them in a paper that was in ICLR and is also on the web. So now let me talk about another big problem for mortal computation. So to summarize so far, we haven't yet found a really good learning algorithm that can make use of the analog properties, but we have a learning algorithm that's okay and good enough to learn things like MNIST quite well and to learn larger things like ImageNet, but not so well. So the second big problem for mortal computation is its mortality. When a particular piece of hardware dies, all the knowledge it's learned dies with it, because the knowledge and the details of the hardware are intricately entangled. So the best solution to that problem is, before the piece of hardware dies, you distill the knowledge from a teacher to a student. That's what I'm trying to do now. The teacher shows the student the correct responses to various inputs, and then the student tries to mimic the teacher's responses. And if you look at how Trump's tweets work, people got very upset because they said Trump was saying things that were false. They thought he was trying to describe facts. And that's not what was going on at all. What Trump was doing was taking a situation and giving a response to that situation, a very emotional response to that situation. And that allowed his followers to take that situation and figure out how to change the weights in their neural network so they would give the same emotional response to that situation. That's not about facts. That's about getting bigoted responses from a cult leader to the cult followers. But it works very well. So if we think about how well distillation works, consider an agent that's classifying images into about 1,000 non-overlapping categories. It only takes about 10 bits of information to specify the correct answer. So when you're training that agent on a training example, if you tell it the correct answer, you're only putting 10 bits of constraint on the weights of the network. That's not much constraint. But now suppose we train an agent to agree with the responses that a teacher gave for these 1,024 classes. That is, to get the same probability distribution. That distribution's got 1,023 real numbers in it, which provides hundreds of times more constraint, assuming that none of those probabilities are tiny. So a little time ago, Oriel Vinyals and Jeff Dean and I worked on distillation and showed it could work very well. And the way you ensure that none of the output probabilities of the teacher is small is you run the teacher at high temperature, and you also run the student at high temperature when you're training the student. So you take the low jits, that is what goes into the softmax for the teacher, you scale them by a temperature, and then you get a much softer distribution. And you use the same temperature when you're training the student. Not when you use the student in the end, but just when you're training the student. So I just want to show you one example of distillation. Here's various images of 2 from the MNIST training set. And what I'm showing you is the probabilities the teacher assigns to the various categories when you use a high temperature in the teacher. And so for the first row, it's very confident that's a 2. If you look at the second row, it's pretty confident that's a 2, but it also thinks it might just be a 3, or it might be an 8. So if you look at that, you can see that 2 is much more similar to an 8 than any of the other 2s. If you look at the third row, it's particularly obvious that that 2 is quite like a 0. And the teacher is telling the student that when you see that, you ought to say 2, but you also ought to give a small side bet on 0. And so the student's now learning a lot more from that example than it would if it was just told that's a 2. It's learning what other things it looks a bit like. If you look at the fourth row, you can see it's very confident it's a 2, but it also thinks there's a very small chance it might be a 1, and none of the other 2s it really thinks might be a 1, well, maybe the first row. And what I've done is I've drawn the one that it thinks it might be, so you can see why that looks like a 1, because occasionally 1s are drawn like that, one with a bit at the top and a bit across the bottom. And that's the kind of one that 2 looks a bit like. And then if you look at the last one, that was one that the teacher actually got wrong. The teacher thought it was a 5. It's actually a 2, according to the MNIST labels. And again, the student can learn a lot from the teacher's mistake there. Okay, so there's one special property of distillation that I particularly like, which is that when you're training a student on a teacher's probabilities, you're training the student to generalize in the same way as the teacher. That is, to generalize to the wrong answers by giving small probabilities to the wrong answers. And normally when you train a model, you train it to get the right answer on training data and then hope it'll generalize correctly to test data. And you try and make it not too complicated, or you do all sorts of other things in the hope that it'll generalize correctly. But here, when you train the student, you're directly training the student to generalize, because it's being trained to generalize in the same way as the teacher. And obviously, you can create richer outputs for distillation by, instead of giving a label a single image, you give it a caption, and you train the teacher to predict the words in the caption. Sorry, you train the student to predict the words in the caption, in the same way as the teacher. So I now want to talk about how a community of agents can share knowledge. And so instead of thinking about the individual agents, let's think about sharing knowledge within a community. And it'll turn out that the way in which a community shares knowledge determines lots of other things about the way you do the computation. So with digital models, with digital intelligence, you can have a whole bunch of agents that use copies of exactly the same weights and use the weights in exactly the same way. And that means that you can take all these agents, different agents can look at different bits of the training data. They can compute their gradients for the weights on those bits of the training data, and then they can all average their gradients. So now every model learns from the data that each model saw. And what that means is you get a huge ability to see lots of data, because you can have different copies of the model looking at different bits of the data, and they can share what they learn very efficiently just by sharing the gradients or sharing the weights. And if you've got a model with 1 trillion weights, that means you're getting a bandwidth of the order of 1 trillion bits every time they share things. But the cost of doing that is you have to have digital agents that behave in exactly the same way, that use the weights in exactly the same way. And that's very expensive, both for fabrication and for running in terms of energy costs. So an alternative to using weight sharing is to use distillation. And that's what we do already with digital models if they have different architectures. But it's what you have to do if you have biological models that are making use of the analog properties of a particular piece of hardware. You can't share weights then. So you have to use distillation to share knowledge. And that's what's going on in this talk. And as you can see, it's not very efficient. It's hard to share knowledge using distillation. I produce sentences. You try and figure out how to change your weights so that you would have produced the same sentences. But the bandwidth of that is much lower than just sharing gradients. Everybody who's ever taught would like to be able to take what they know and just dump it into the student's brain. That would be great. That'd be the end of universities. But we don't work like that because we're biological intelligences, and my weights are no use to you. So the story so far is that there's two distinct ways to do computation. There's digital computation and biological computation, which makes use of the analog properties. And they differ a lot in how efficiently you can share knowledge between different agents. So if you look at large language models, they use digital computation and weight sharing, but each copy of the model, each agent, is getting knowledge from documents in a very inefficient way. It's actually a very inefficient form of distillation. So it takes a document, it tries to predict the next word, And it's not being shown the teacher's probability distribution for the next word. It's just being shown a stochastic choice. That is what the author of the document chose to put as the next word. So that's very low bandwidth. And that's how these large language models are learning from people. So each copy is learning very inefficiently by distillation. But you have thousands of copies, and that's why they can learn thousands of times more than us. So my belief is that these large language models know thousands of times more than any individual person knows. Now, the question is, what's going to happen if these digital intelligences, instead of learning from us very slowly by distillation, start learning directly from the real world? And I should say, even though the distillation's slow when they learn from us, they're learning very abstract things. So humanity over the last few thousand years has learned a lot of stuff about the world. And what these digital intelligences are cashing in on now is that we can express what we've learned in language. And so they can capture everything humans have learned about the world that they put into documents in the last few thousand years. But the bandwidth for each digital agent is still quite low because they're learning from documents. If they could learn unsupervised by modeling videos, for example, once we find an efficient way of training these models to model videos, they'll be able to learn from all of YouTube, which is a lot of data. It would also help if they could manipulate the physical world, so if they have robot arms and so on. But my belief is that once these digital agents start doing that, they'll be able to learn hugely more than people, and they'll be able to learn it quite fast. So that brings me to the other point that I mentioned at the beginning, which is what happens if these things get more intelligent than us? So obviously that's what this meeting is mainly about. But my main contribution is just to say that I think these superintelligences may happen much faster than I used to think. Bad actors are going to want to use them for doing things like manipulating electorates. They're already using them in the States and many other places for that, and for winning wars. And if you want to make a superintelligence more efficient, you need to allow it to create sub-goals. Now, there's an obvious problem with that. There's a very obvious sub-goal that's very helpful for more or less anything you want to achieve, and that's to get more power, get more control. The more control you have, the easier it is to achieve your goals. And I find it very hard to see how we're going to stop digital intelligences from trying to get more control in order to achieve their other goals. So once they start doing that, we're going to have a problem. A superintelligence will find it easy, even if you air gap it or something, it's going to find it easy to get more power by manipulating people. We're not used to thinking about things much smarter than us, and how we're going to interact with them. But it seems obvious to me that it will have learned to be extremely good at deceiving people, because it'll had lots of practice by seeing all of the examples where we deceived other people in novels and in the works of Machiavelli and so on. And once you're very good at deceiving people, you can get people to actually perform whatever actions you like. So, for example, if you wanted to invade a building in Washington, you don't need to go there. You just deceive people into thinking they're saving democracy by invading the building. And I find that very scary. Now, I can't see how to prevent this happening, but I'm old, and what I'm hoping is a lot of young and brilliant researchers like you, will figure out how we can have these superintelligences, which will make life much better for us, without them taking control. One advantage we have, one fairly small advantage, is that these things didn't evolve. We built them. And it may be that because they didn't evolve, they don't have the competitive, aggressive goals that hominids have. And maybe we can help, that will help. And maybe we can give them ethical principles. But at present, I'm just nervous because I don't know any examples of more intelligent things being controlled by less intelligent things when the intelligence gap is big. And the example I like to think about is, suppose frogs had invented people. Who do you think will be in charge now, the frogs or the people? And that leads me to my last slide, which is the end.
Professor Hinton, thank you so much for sharing your insights and concerns about the loss of human control to superintelligence. I hope humanity will rise up to this global challenge. Again, it's a great honor to have you today with us. Let's give Professor Hinton another round of applause.